10.4, using the Pythagorean Theorem. This is going to be broken up into two sections. The first section is learning what the converse of the Pythagorean Theorem is. The second section is learning something called the distance formula. So the converse of the Pythagorean Theorem, you need to make sure you write this down. So let me explain it to you, and then I want you to write it down on your paper as you pause the video. The converse of the Pythagorean Theorem is taking what we already know, which is a squared plus b squared equals c squared, and actually using it to prove if a triangle is a right triangle or not. Because remember, right triangles are what we must have to use the Pythagorean Theorem. So if we reverse that and we're given the sides, we can then prove whether or not a triangle is a right triangle. So here's what the converse of the Pythagorean Theorem states. If the equation a squared plus b squared equals c squared is true for the sides of a triangle, then the triangle is a right triangle. So pause the video and write that down. So let's now do an example. I'm going to give you three different sides of a possible right triangle. 24 meters, 25 meters, and 7 meters. This is actually incredibly easy. We have three sides, 24, 25, and 7. We're going to plug them on into A, B, and C and see if it's true or not. But remember one thing. That C squared, has to be your hypotenuse, which is your biggest number. So just because the 24, 25, and 7 are in order here, you don't put them in that order into A, B, and C. You got to put 25 in for C. So I always think it's easier just to put A as your smallest number, B as your next smallest number, and C as your biggest number. Now remember, 7 and 24 can be interchangeable because the legs, it doesn't matter what you plug in for A or B. So now we just simplify. 7 squared is 49. 24 is 576. And 25 is 625. 49 plus 576 is 625, which does equal 625. Therefore, yes, that does work. And yes, these three numbers are a triangle. Now, let's say this is number A. Part B, let's plug in 9, 4, and 8. So do that one on your own and see if it's a right triangle. You will notice that if you plugged in 4 squared plus 8 squared equals 9 squared, that would give you 16 plus 64, which gives you 80 equals 81, which is not equal. Therefore, no, those three sides, 9, 4, and 8, do not make up the sides of a right triangle. Example number 2, I just want you to watch. You do not need to write this down. Find the distance from point A to point B. This is where the applicational use of Pythagorean theorem becomes a little more tricky. So I want to find the point for the distance from point A to point B. That's all we have as a segment. So how would you go about finding the distance from point A to point B? Well, you have a coordinate grid, and this grid tells you the location of points. So you know this A is at 1, 1, and B is at 4, 5. Well, what you can do is make a triangle out of this. Because that's a right triangle, all you need to do now is realize that the base here, or the bottom of your triangle, has 3 units. This other leg is 4 units. So we know we have legs of 3 and 4 units. And the distance from A to B can be represented by the hypotenuse, which is our C. So we know that we have 3 squared plus 4 squared equals c squared. 9 plus 16 equals c squared. And 25 equals c squared. Square root of both sides. The value of c is 5 units. Now, something you might need to know, actually you do need to know this. This would be a 3, 4, 5 triangle. And I'm not sure if I've mentioned this yet, but that's something called a Pythagorean triple. So I would suggest you write that down. A Pythagorean triple. It is actually the most common used set of three numbers that make a right triangle. So 3, 4, 5. Always remember that. 3, 4, 5, 3, 4, 5, 3, 4, 5. 3, 4, 5 is the most commonly used Pythagorean triple within the Pythagorean theorem. So keep that in mind. Whenever you see like a 3 and a 4 as legs, 5 is going to be the hypotenuse. If they give you a 5 with a leg of 3, 4 is going to be the other leg. If you get a leg of 4 with a hypotenuse of 5, then the other leg is going to be 3. Example number 3. This one you do need to write down. Find the distance from point A to point B. Now A is 1, 1 and B is 4, 5. And if you remember, we just did this exact same problem. This problem we did in number 2, except I gave you on a coordinate plane. A is 1, 1, B is 4, 5. Now if you look here, 1 to 4, that's a change of 3. 1 to 5, that's a change of 4. So we know right here we have a 3, 4, 5 triangle. The missing side from A to B, or the point from A to B, which is our hypotenuse, is going to be 5. But there's another formula that you must memorize. And this is called the distance formula. The distance formula is the distance d between any 2 points, x sub 1, y sub 1, and x sub 2, y sub 2, is given by the formula d equals the squared root of x2 minus x1 squared plus the difference of your y values, or y2 minus y1 squared. So basically, all this is saying is you subtract your x values, square it, subtract your y values, square it, add the two terms together, and then you take the square root of what is left. So we're going to use the distance formula on 1, 1, and 4, 5. So 1, 1 and 4, 5. Let's let 1, 1 be our first x and first y values, and 4 be our second x value, and 5 be our second y value. So all we do is plug it in and simplify. So our x values would be 4 minus 1 squared plus 5 minus 1 squared. Now before we go any further, keep in mind that you may say, well, I'm going to let 4, 5 be my x1, y1. That's fine, because if you take this 4 minus 1, that's going to give you 3. 3 squared gives you 9. If you did it backwards, 1 minus 4, that gives you negative 3. If you square that, that's also going to give you 9. So either way, you're going to get the same answer. So this is going to give us d equals, and then 4 minus 1 is 3 squared, plus 4 squared. D equals 3 squared is 9, plus 4 squared, which is 16. 9 plus 16 is the square root of 25, and the square root of 25 becomes 5. So once again, there is yet another method to find the distance between 2 points. You can use Pythagorean theorem, or you can use the distance formula, plug in your values, and simplify it. And in this case, we get d is equal to 5. So the distance from point A to point B is 5 units. Number 4, write down the 2 points negative 3, 5, and 2, negative 1. We are going to find the distance between them. Using our distance formula, d equals the square root. We are first going to subtract our x values. So if we subtract the x values, negative 3, 2. So let's subtract 2 minus negative 3 squared plus subtracting our y values, negative 1 minus 5 squared (2 minus negative 3, that becomes 2 plus 3. So that would be 5 squared, which is 25. I did skip a few steps. If you don't want to, that's okay. Now we're going to add negative 1 and negative 5. That gives us negative 6 squared, which gives us 36. We add 25 plus 36, that gives us the square root of 61. And if we round that to the nearest tenth, you would get 7.8. Now the book, or if you're checking your answers, the book is going to leave it as the square root of 61. We have not done the radical unit yet, so you do not know how to simplify radicals. So I would be perfectly fine for you to round to the nearest tenth and give me 7.8. This example is from your book. You do not need to write this down, but this is where it gets a little difficult. This requires quite a few steps. So a football coach designs a passing play in which a receiver runs down the field, makes a 90-degree turn, and runs to the corner of the end zone. A receiver runs the play as shown. So if you look to the left, there is a graph here. It shows us that the receiver starting right here where my arrow is, that's at the point 60-50. Runs down at the point 20-10, turns, and goes towards the corner of the end zone. Here's the end zone in blue. And that's represented by 80-30. Did the receiver run the play as designed? Each unit of the grid represents 10 feet. So here's the problem. I want to know if that's a right triangle. Well, in order to know that this is a right triangle, you have to first know all the distance of all three sides. The problem is that you cannot count using this grid, because if you look from where my arrow is, from the starting point to the turn, it's not straight up and down. It's not vertical or horizontal with your axes, so you can't just count the boxes. So you're going to have to use the distance formula 3 times and determine the length of each of the 3 sides. Now that's done for you right here, and I'm going to write it down just so you can follow along. So the first one, we are going to take the point 60-50, which is where he started, to where he turns, which is 20-10. So let's subtract right here. We're going to take 60-50 and 20-10. Let's subtract our x values. 60 minus 20, I'm just going to do a shortcut, is 40 squared. Plus, subtract our y's. 50 minus 10 is 40 squared. 40 squared plus 40 squared gives you the square root of 3,200. Now I'm not going to change that to a decimal quite yet. So let's go on to the next one. Now, he's at the point where he turns, which is 20-10. He then goes to the end zone, which is represented by the point 80-30. So let's subtract here. Now once again, it does not matter the order that you subtract these. So I'm going to just take 80 minus 20, subtract your x values, 80 minus 20, that gives me 60 squared, plus negative 30 minus 10, which is negative 40 squared. That would give me 60 squared, which is 3,600, plus 40 squared, which is 1,600. That gives me the square root of 5,200. Last, we have to connect the starting point to the end zone to get the third side of the triangle. So we have 60-50, and we have 80-30. Subtract your x's. 80 minus 60 gives you 20 squared. Negative 30 minus 50 gives you negative 80 squared. And that would give you d equals 20 times 20 is 4,000, plus 80 times 80, which is 6,400. I'm sorry, 20 times 20 is not 4,000. 20 times 20 is 400. 80 times 80 is 6,400. You add those together, that gives you 6,800. Now, this is the part that you got to think. We have three sides. Now, these are exact values. If you round them, they are no longer exact values. And while you still can do the problem, let's say you rounded these to all to the nearest tenth, that's fine. But then the next step, it would have been exactly accurate. So we are leaving these three square roots alone. So what do we need to do? Now, what do you think we need to do here? Well, let's read our problem. We are determining, did the receiver run the play as designed? Well, how was the player supposed to run the play? The player was supposed to run down the field, make a 90-degree turn. So what we're really determining is, did that player make a 90-degree turn? Well, what we're doing is proving whether or not these three sides make a right triangle, which is the converse of the Pythagorean theorem. So we have to plug all these in to a squared plus b squared equals c squared. Because 6,800 is the biggest value, the square root of 6,800, that's going to be our c. So we're going to plug in the square root of 3,200 squared plus the square root of 5,200 squared equals the square root of 6,800 squared. The square root of 3,200, if you did that on your calculator, the square root of 3,200 and then squared it, you will notice that's the exact same thing, because the squared root and squared are complete opposites or inverses of each other. So they cancel each other out. So 3,200 plus 5,200 equals 6,800. 3,200 plus 5,200 is 8,400, which is equal to 6,800. They are not equal. Therefore, right here, that is not a 90-degree angle, and therefore, no, this player did not run the play as designed, because we do not have a right triangle.